Hi, this is Steve Bake, and for our physics video project, we're going to do a problem about a truck. Actually, Steve's in the truck right now with his friend Chelsea, and he wants to get closer to her in a romantic type of way. So he's going to drive and turn, trying to use the force of physics to pull her toward him so that they can be closer together and, have a little romantic juice going, I guess. Anyway, let's see which direction Steve has to turn so that she goes toward him instead of away from him. All right, Steve, go ahead. Right there, Steve turned to the left, which was a mistake because turning to the left pushed Chelsea away from him instead of toward him, because she continued in the motion of the direction she was going because not enough force was applied on her to stay in her seat. So she was actually pushed away from him instead of toward him. So that wasn't the right direction to go.
Now Steve's going to try the other way to see if him turning right will make Chelsea slide towards him. Okay? We see that the force turning right would be the correct way to go because the force was strong enough to pull Chelsea all the way over closer to Steve. So it works.
As we found out the other day, if Steve turns to the right, he can pull Chelsea toward him using the force of the turn. This can be done by two equations. The first of which is F of S, which is the static friction, equals mu of S times the normal force N. You can also find the sum of all the forces by doing sum of the forces equals Chelsea's mass times her acceleration around the turn.
Chelsea's acceleration is equal to the car's acceleration, so we use the equation A rad, which is equal to the radius of the circle of the acceleration, equals velocity squared over the radius. In the absence of friction, Chelsea moves in a straight line to the left when in a right turn.
The free body diagram for this equation goes like this. Static friction equals mu of S times the normal force in the x direction. In the y direction, the normal force pushes up, and then mass times gravity is pushing down. And then for the sum of the forces of this equation, in the y direction, it's ma, and then that what the? And that gives us the normal force equal to mass times gravity. Okay, the sum of the forces in the x direction is max, and that gives us mu of s times n equal to ma rad. And a rad equals v squared over r. If the coefficient of static friction between Chelsea and the car seat is 0.55, and I am driving at a constant speed of 15 meters per second, we can find that the max radius of the turn I can make and still have Chelsea slide my way is...
Okay. We are now given enough information so that we can see the maximum radius of a turn that Steve can make. Since it's driving and it's going in a horizontal direction, we use the sum of the forces in the x direction. So we're using mu sub s times n here, which n also equals mg in the y direction, mu sub s times m times g equals m times a, which a equals v squared over r. Now I'm going to solve this equation so that we're solving for the radius. So you multiply both sides by the radius, and then I will divide by mu sub s times m times g to get rid of that. And I'm left with the radius equals mass times velocity squared over mu sub s times mass times gravity. And I can get rid of the masses because they cancel each other out. So now I'm left with an equation that I can substitute in the values that were given. So the radius equals 15 meters per second squared over the coefficient of static friction times gravity, which is 9.8 meters per second squared. The answer we get from solving this equation is 42 meters. So the maximum radius that Steve can make while turning to the right is 42 meters. That way I still slide to him and sit next to him on the seat. This makes sense because the larger the coefficient of static friction, the smaller the radius is going to be.